Hey guys, I wanted to do a, well, maybe not so quick video about an interesting tool for use inside of Unity, the editor itself. And this is a mesh retopology tool using constrained elastic surface nets, which is a type of voxel system. So just going to jump right in and show what it does, and then get into the detail about how it works a little bit. There'll be a detailed section in the video, and that's for people who are interested in using the script for their own purposes or improving it or whatever, understanding what it's doing. It's a very interesting field. What this script does by itself is pretty basic. So let's show that. So here we have this cave type thing. And for purposes, I mean, like this was just kind of slapped around in Modo very quickly. It's just sort of like a little, feels like you're back in Ankaraji. And okay. And actually this one's flipped just so we can start the video inside something and get a sense of what we're talking about. This is mostly for interior modeling. So I'm gonna turn that one off, turn the original giant turd looking one on, and go to game object, retopologize game object via constrained elastic surface networks. Oh boy. And well, surface nets actually. All right. Well, when I started developing this, the grid size was set pretty low because meshes themselves are pretty small. This thing is quite large, so I'm using a grid size of 6. But otherwise, it's the defaults and create. Take a second. Okay, here we go. That is the retopologized version of the original mesh. And so we'll look at the original mesh vertex triangle counts. We see that this had 22,000 verts and almost 40,000 tries, and the new one has a little bit under 8,000 verts and just over 7,000 tries. So not as much of a vertex reduction, on about a third as many verts, but quite a decent reduction on triangles and polygons. And looking at the quality, I mean, you know, it's pretty good. It is definitely, you can see here where there's a cleft and this kind of, not really face, but this is some detail here that didn't really come across the nose, kind of did, nothing else really did. Some squiggles in here that just didn't really make it across. I'm not entirely sure why, because there is actually a decent amount of detail there. It seems like it could have done a better job, but sometimes it's just like that. And then visually comparing the vertex density, I mean, you really can very clearly see the advantage of doing this. Okay, so then let's take a look at, now we have this thing, we want to make it back into a cave though, and actually this will help illustrate, I guess I'll show another part of this thing very quickly. These are secondary scripts, they're not really part of the retopologizing, but when you're doing this type of retopologizing, you might want to have like a reason for it. So in this case, we bring this original mesh in, although Modo did a pretty decent job, even just kind of slapping this thing around, let's pretend that it had a really high poly count. It does, pretty much. And that also the polys were very unevenly distributed. I mean, in this case, they are quite evenly distributed, but they could be completely arbitrary, all bunched up and whatever. And also doesn't really have any useful UV information. You can see that it's got this kind of Bryce Canyon effect on this cave texture here. It just really doesn't look very good. And this always happens when you just kind of sub-D model something like this. It's not going to have useful UV data without quite a bit of work. So in practice, we want not only to simplify our mesh, but also to get some more sort of game-ready asset out of it. So we drop the cave model, the cave texture on this, and we see that, well, I mean, it's improved a little bit, not really. What this has done in the script that does this, it just does a planar top-down Y UV projection on the mesh. So it's, you know, not completely useless, but it does have this streaking, which is kind of a big problem. So another tool that we can use, again, this is separate script, but it's worth discussing in the same breath because it was all part of the same workflow from my perspective. Generate boxed UVs, and this kind of is doing like, it's like static triplanar mapping. For every face in the source mesh, it's going to consider, well, which cardinal axis is that face most aligned with, regardless of orientation, you know, plus or negative, just going to be which one is it mostly aligned with. And then it's going to put it in sort of a planar projection in that axis. And all those planar projections are just going to be overlapping in the equivalent of world space in UV space on whatever plane you're projecting on. So click that. This one is dog slow. I made some mistakes somewhere. The script is doing basically nothing, and it just takes a day and a half. I don't know why. I need to look into what's going on there. So now I have this. Okay, I'll put the cave texture on that, and right away you can see, oh, that's nice. We have, well, it's better to see it on this side, I guess. No more streaking, and it looks pretty decent from any angle. I mean, it's doing the triplanar thing, sort of, even though it has hard seams. You can probably see here on YouTube, try and get it zoomed in a little bit better, what a mess the seams can be. One thing to keep in mind about the script for debug purposes, this UV script does also, it writes UV colors to the mesh so that when it decides which axis something will be aligned on, it also colors it by that axis so that you can, drag this vertex colors shader out and see, what it thinks of the faces. And you can see how rough some of these edges are. I mean, this is just, it's trying to be mathematically accurate. It could probably have like a greedy rule, which, wouldn't be too hard to implement, and that would sort of prevent some of these pops. But sometimes you want the pop to exist. I mean, that stuff actually matters. Anyway, all right, and then the last tool, just to make this a cave again, something that we started the video with a cave. We're going to edit this part of it with a cave by flipping normals, another script in this whole process. I'm going to delete this one. I'm going to turn this one off. Set this down on Y. And go to the perspective of our dude. So here we are, we're dude. And we went from this, which, very high vertex density, very nice, but can't be textured. And it's too high vertex density and may have irregular distribution, while this one doesn't. We went from that to this, which is, regular vertex distribution, very low poly, relatively speaking, and extremely easy to texture, just because of the triplanar mapping, or the fixed triplanar mapping. Again, I mean, seems good, maybe a place to put props, bushes, weapon racks, anything you possibly can. There's one ugly spot down here. I mean, it doesn't look so bad, but as you go all the way down here, I have this little other guy down here to highlight this area here. I'm actually going to put the default shader back on because, oh, well, nope, put the cave shader back on. You can see just how grungy this thing can get in its interpretation, and you do need to watch out for that, because, I mean, the original at this point really doesn't look that bad. So I'm, it's got its weaknesses, but overall it's pretty good. You can export this as OBJ. You'll lose vertex colors, but actually, since the UV script in particular is currently destroying them, I would certainly recommend that you edit that out if you use that script. Anyway, yeah, you would export this as OBJ and be able to iron some of this stuff out in a program, Moto, Max, Maya, whatever you want to use. These seams you're going to have a hard time getting rid of because the UV islands are done a certain way. You could do like a pelt mapping scheme or whatever, in which case, not entirely sure how valuable any of this is. But, so there we go. That is the process. That is what we want to end up with, and we end up with it. It takes like no time at all to generate stuff like this, when you can be very sloppy in your modeling, do no UVing at all, come in with this giant ass mesh that has all kinds of problems, slap it in here, and end up with something that actually, although not beautiful, could be used in a game basically instantly. All right, that's the overview. And if you're going to do that, if you're interested in taking this project and using it for that purpose, the scripts you're looking for are the Wizard Retopology Constraint Elastic Surface Net CESN. I'm going to be calling it CESN for the rest of this. And the poly test utils, and I think that's all you need. I would strongly recommend keeping the box mapper, deep copy, and flip normals as well. These are sort of a package. I mean, they're not really, but I would think of them as a package. So these are really the two necessary ones: the Wizard Retopo CESN and the polytest utils. Okay. So that's the practical side of this, and I want to talk a little bit about the theoretical side of this, because it's a pretty interesting field, all this retopologizing. So let's delete this mesh and let's go back to our original. Let's talk about what CESN actually does. So this time I'm going to put the default shader back on. This time I'm going to run the retopologizer. I'm going to turn smoothing off though. So this is going to be there's a whole sort of convolution phase or deformation phase, and if you don't run that, what you end up with looks like Minecraft, this floating box city thing here. And this is a voxel representation of the surface. A lot of these retopology systems begin with something like this. What this stuff all has its origins in, in medical imaging, and voxels are basically a way of trying to parametrically resurface. Usually it would be an implicit mathematical surface, what they call an isoparm, which just means isoparametric, and that's basically talking about something like you might have a function that from world space origin, f of x, y, z is just going to return, 1 over the distance to world space origin as an intensity at that point. So this is basically a radial gradient fall off from world center. And then you might have an ISO function which says, okay, well, when that fall off falls below 0.5, consider that an edge. Consider that a function crossing or a zero crossing. Well, actually, I guess it would fall below 0 would be the zero crossing. That one's asymptotic, so it won't. But modified to have a zero crossing. Basically, you define rules where when an ISO surface, one of these mathematically defined, purely defined fields, crosses the surface, then that's where you would consider that to be the skin of the surface. And so a lot of these voxelization systems rely on that. Now, you may notice that this system that I'm using here is quite primitive, right? I mean, this isn't allowing us, and maybe I should have said this up front, this is not about dynamic voxelization. This is not about being able to tunnel through the world in real time. You might be able to get somewhere like that with this system, although I think this would be probably not the best way to start for that. But this isn't about one of those, crazy tunneling systems. This is just about retopologizing a mesh with certain rules inside Unity. It can be extended in a number of directions, but this implementation as presented is relatively primitive. It's really just a retopologizer. And the other thing that's interesting about it is it's not working on algorithmic data. Now, when you see people doing that, tunneling their way through the world, on YouTube, there's a lot of videos with this kind of stuff going on in voxel terrain systems. What those actually are is, take this this Minecraft looking mesh up here and pretend that this started out as just like a ball, like just this little lump section here in the middle. And what they're basically doing, this is called a binary field. What they're doing when they're painting is they're adding to the binary field. It's like making a snake out of it, just like this actually. And then that is getting multiplied against a 0 or 1, and it's getting multiplied against world space per lin noise, just a big, crazy fractal type pattern. It's not really fractals, and most per lin noise is per lin noise, which is anyway, this big organic pattern spreading out in all directions, and it's being multiplied against this binary field, and then that's being tested against an isoparam function, and that's what's building that kind of crazy geometry that you see in those quick world editing videos. This is similar. It's not doing the same thing. What it's doing is it's dividing the world up into a bunch of grid cells, which are basically the voxels. And actually, well, technical point, voxel means something that doesn't really have to do with the cell. And I use the two interchangeably, and I really shouldn't. I'll try and say voxel cell when that's what I mean. So it's going to divide the world into a bunch of voxel cells. And then it's going to build this skin, basically connecting the centers of the surface cells, the cells that are well, I'll get into what's the difference between a surface cell and an almost surface cell in a moment. So you end up with this Minecraft-looking skin, and then what, regardless of whether you're using, marching cubes, marching tetrahedron, in this case, constraint elastic surface nets, you want to basically deform this area of these binary intersections. You want to melt that down into something approximating the original shape. In the case of constraint elastic surface net, the implementation used here, let's look at my mouse is getting caught on something, kind of driving me a little crazy. All right. If you look at this point here, it's a clear, obvious one, like this one right here, this vertex, that is actually sitting at the center of a voxel cell. So every cell, when you look at this mesh down here, it's put inside a bounding box, and then it's divided up into a number of cells, which are going to be the voxel cells. And at the center of every cell, a point is drawn. If those cells are surface cells, then quads are drawn connecting the center points of the cells, and that's basically all this is doing. Then what it wants to do is it wants to reposition those center points with the quads, sort of attached to them, such that they conform to the underlying mesh. Now, actually, the way this is done is the quads aren't drawn until after that process, but just conceptually, you want to think of it as making this big, ugly-looking box thing, which isn't all that ugly, but a box-looking thing, and then kind of, pulling it down to fit around the original mesh. Now, the constrained term in constrained elastic surface net just means that if this point is inside you imagine there being an offset grid. This is what's called a dual contouring, and the dual comes from the fact that there are two grids. Because these endpoints are actually the center of another grid, there's another grid that looks exactly like this, offset by half a unit, which contains this one, basically. And you want to think about, okay, if this point right here is the center point of a voxel cell, which is drawing quads out to its neighbor center points, The constrained part is that when we do our approximation of the underlying surface, when this thing is averaged towards that surface, it can only move around inside its parent cell. It can't go outside. That's the constraint of the elastic surface net. And for practical reasons, I ended up relaxing that constraint, and I will demonstrate why. So let's do a couple things. First off, well, actually, yeah, I'll demonstrate why we relax the constraint real quick. So I'm going to do this again. Retopologize with CESN. Max it. Well, I'm going to turn smoothing off. Put this on 6. And there's really not much point doing a side-by-side because you'll see the effect right away. Oh, sorry. I'm just an idiot. That's not what I meant to do. That certainly isn't very smooth, but that is not the way this was supposed to work. The way this is supposed to work is that this pass gets cut out. Yeah, I think it's just this right here. Okay, so in the CESN, don't do that. Or no, do that, but it won't do it all the way this time. Your voxel surface. And you can see right away. I mean, you don't even really have to remember that. You can see this looks like a Michael Aram artwork or like hammered bronze or something. It's kind of cool, and in some cases, actually, it might be the desired effect because it does have a little bit more surface irregularity. It looks a little bit more like rock. Actually, this might make the better cave, all things considered. I mean, it's kind of cool, but it's not particularly smooth. So I ended up using a second, and I'll get into the code in a minute, but you can see here, this is a second pass. Coarse destructive smoothing pass. Voxel constraint no longer applies. This is just, you know, Laplacian neighboring algorithm, nothing to it. So if we use that, and go back in here. Now, one thing I do want to demonstrate, when you're doing this kind of retopologizing, there's always a question about how do you actually build the surface. And the original CESN paper talks about using, everything's based on triangles and triangle pairs. And what is pretty easy to find out when you're implementing this is that naive triangulation doesn't look particularly good, and you're better off trying to work in quads and then using quad subdivision rules, usually what's called a minimum distance subdivision rule. So basically you look at the quad and you say, well, I want to draw an edge through this quad to turn it into 2 triangles, but I want to draw the shortest edge that I can. And we'll get to how that happens in a minute. So I want to retopologize again. Oh, well, actually, I'm completely lying. I do lie a lot. I don't mean to. It just happens. I'm a terrible person. All right, there we go. We got this. So now it'll actually work. I'm going to run this. This is exactly the same settings that we used to generate the first version of this in the beginning of the video. All right, voxel surface. I'm going to do it again, only this time I'm going to use this sort of outdated one, the retopologize via CESN no quad. So this is one that's going to do naive triangulation, just to demonstrate the difference between the two approaches to surfacing. All right. I think it's actually most visible on this side. You can see there's lots and lots and lots of spurs and stars in these. Okay, well, there's also lots of gizmos hanging out on top of these things, but you can see all these spurs and diamonds and stars and things that look like, you know, like dandelions, whole rows of them actually. Whereas on this is the naive triangulation. Whereas on the quad minimum distance split, it's a very even surface. We don't have a lot of, we still have some artifacts, so it's jumbled up here, but it's just nothing like the mess that we have up here. This area, yeah, this whole area here in particular. Actually, where is the, well, there was a part I wanted to focus on for the video, and of course now I can't find, now it's working great, you know. It's like no problems at all. It's actually still got some problems though. And you can see, you know, just again, up here are these rings and splits and stuff, and how much cleaner this bottom mesh looks than that. However, it's also worth pointing out that in practice, they're not like, I mean, they are different. You can definitely see this is a much smoother edge than that. This is a smoother edge than that, even where it has trouble. Those look basically okay. This is a little smoother here, much smoother here. But it's not the end of the world. I mean, even if you use the naive triangulation, it's not like that's going to be why the mesh looks terrible. So, you know, that's interesting. And you still, I mean, even with this improved method, you do still get some obvious spurs like that. And I mean, you could probably beat that. I haven't put a lot of effort into surfacing. It's a pretty deep and interesting field. So for that matter is voxelization. This started out as like, one of those, oh, wouldn't that be cool? And turned out to be, yeah, maybe, but it took a very long time. And I didn't ever finish it. And then I just got the sort of second wind to finish it last night. And I actually did an original video of this and hadn't at that point done the quad surfacing, and was looking at the video again. I was like, I make a really good point about how bad this is. Maybe I should revisit that. And I probably shouldn't have actually spent the time on it, but it didn't take very long, and now it looks a lot better. So, all right. So that's all that, and now that we have, we almost have all the conceptual stuff in place to go look at the code for anybody who is still listening and cares about looking at code. I do, though, just want to also show the debug content, which is kind of interesting. This hopefully won't crash. There we go. All right. Voxel container. This bunch of cubes, these are the cells that are created. These are the cells that basically contain the centers. These are the cubes where the center points of these cubes want to be joined to form the underlying mesh. So this is one grid cell, and the other one is the other grid, and that's that dual contouring you read about. I think, I'm certainly not good at anything, so I think that's true. An interesting point I wanted to make here about this process is first and foremost, well, it'd be difficult to really see this, I think. Let's see, maybe a little bit here. This thing's hollow. You can see that we're only getting surface cells. And specifically, we're only getting useful surface cells. And by that I mean, remember, we want to be able to draw polygons out from the center point of a cube to another center point. Well, that means that every detail has to be at least 2 enclosing grid cells wide, so we can draw an interior grid chunk around them. Like, everything has to be thick. They can't have any like just fins or any polygons floating in space. They have to form an enclosed surface. So obviously, when you have things like these two guys up here who are just kind of floating out on their own above the rest of the surface, no matter how you draw a polygon between them, it's just going to be planar. There's no way for it to have any depth because there's no neighbor to connect to. How does something like this happen? Well, what happens is the way the script works, and again, this is not very different, but it is different than the way these mathematical scripts work because it has to deal with some of the vulgarities of mesh data and not everything being purely algorithmic and beautiful all the time. So one of the vulgarities of mesh data is it's all made up of, meshes and triangles and stuff. So what this thing does is it goes and gets every triangle in the source mesh. So it's looking at this thing down here. At every triangle, it says, okay, well, what's the bounding box for this triangle? Which grid cells, these things, basically, in their conceptual form, which of these conceptual grid cells is the bounding box of this given triangle contained within, or what intersects it, basically. So where do we have potential intersections between the mesh and the voxel grid? And then we're going to need to actually do a real test to see, like, well, does the triangle actually pass through the interior of the grid cell at that point? Because, the bounding box might, like, you'd have a triangle at an angle and it creates this kind of weird-looking bounding box, and that might clip another bounding box, even though the triangle does not, in fact, bisect any edge on that other mesh. Now, looking here, we can say, okay, this edge in between these, you have these 2 yellow cubes, and there's this bottom edge between them. It's entirely possible that a triangle did bisect that edge. In fact, 2 of them would have to have done that. But what happened is it only bisected the edge. It did not, in fact, envelop any of the corner points. And the corner points are extremely important. All of the inside-outside tests are done on corner points, not anything else, not the center, not the middle or anything. There is a way of speeding this up. If you look at, there's a guy, Mykola Lysenko, 0 FPS. He has a certified AAA Platinum Genius implementation of this. His works a little bit differently because his is basically, it's like CESN / marching cubes. But he has a very, 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 very dense and good representation of insidedness testing and winding order testing and edge and corner intersection all done in like this one very compact test. But the way I was doing it and the way with working with the mesh data doesn't really work that way. So again, the mesh might have overlapped this edge between these 2 cells, but it wouldn't have overlapped. In this case, it obviously didn't overlap the corner, because if it overlapped this corner, there would necessarily have been more, other cells would have been intersected by that same polygon. So we can see here it didn't intersect the corner. It only intersected the edge. These two guys can't form anything. So they're coded. They're just, the debugger codes them as yellow. The thing I wrote just codes them yellow so we can see what's it pruning. And this mesh, you know, played by the rules. Didn't do anything too crazy. I had meshes that came in not looking so hot. You know, test meshes that were intended to be disrespectful of the process, and certainly were. So, okay. And let me grab the actual voxel surface. So there's our concepts. So again, we got this thing, bounding box, subdivide, test, polygon test, and then actually there's an interesting test which I'll get into when we start looking at the code. So let's look at the code. Let's do that. And if you don't have an interesting code, sorry, this is, I just feel like, you know, this stuff is, the tool itself is useful, but to me what's interesting about this is the process and being able to extend this to do pretty much anything. And even if this particular tool isn't like the coolest thing in the world, you could obviously retopologize. You could take this mesh out of Modo, put it in ZBrush or anything, retopologize it there, and just use the planar UV thing, or even just a triplanar shader, and not deal with any of this at all. That would be perfectly fine and perfectly reasonable, except that then you wouldn't be working towards a toolkit that lets you build user editable content. You wouldn't be working towards having your own kind of standard tool suite that just runs in your game engine. You look at a game like WoW. WoW is built almost entirely from within the game engine. Like they basically rebuilt a combination of Unity IDE, Studio Max, their own custom thing, gobs of quest editors and all that in the client. You know, so they had to build all these tools. And I'm kind of obsessed with that. I mean, I'm not actually able to pursue that idea really because, you know, full time I have to do other things, but I think it's the way to live. And every time I can get something that works, that's intelligent, is closer to that, I'm very happy with it. And I just wanted to share this one because I think this could be very useful for a lot of people. It's a way of thinking about things that can be very useful. All right, enough bullshitting. On to the code. There is a bunch of debug stuff in here because debugging, when I started working on this, debugging was extremely helpful to understand what it's actually doing. All right. Again, we get the bounds around the, oh, by the way, it's only going to consider one object with one mesh. Nothing fancy at all. This is considering one object with one mesh. Okay. You could, I mean, it wouldn't be all that difficult to beat that. All right. There's a qualification to that I'll get to in a moment. Stick to one object, one mesh, and the mesh has to have some things, you know, some things have to be true about it, which we'll get into in just a moment. So you go to render bounds, and then we're going to divide the bounds to get the number of cells we're going to build at a given voxel density or voxel size, you know, grid size. Not terribly confusing here. One thing that's worth pointing out, all of the cells are all counting their position. A voxel's position is given by its grid cell position, and the grid cell position X, Y, Z values are all relative to the object's bounding box minimum. In other words, every grid cell is going to have a strictly positive, well, including 0, X, Y, Z position value, and therefore also ID, because the position is the ID. And just as another note, if you're looking at this code and thinking like, Jesus, could he bother optimizing this at all? Yeah, probably, but this is not optimized. So if you look at this and it's just not optimized very well, no, it's not, and it certainly could be done a lot better. Especially if you want to use this real time, there's a great many things you could do to speed this up. Okay, so here we are. Like I said before, we're going to iterate through every triangle in the mesh. I do use some, again, talking about optimizations, I have some structs up here, triangle struct, vertex struct. These are things that just kind of help managing metadata and doing some specific modeling and support stuff that I wanted to add without having to think too hard about it. So I do use some pretty brutal, heavy-handed approaches to storage. But anyway, we go through, here's the loop where we have our triangle, we get its bounding box, we go through the cells only that we think we're going to hit. We basically build a bounding box. It's like a bounding box of bounding boxes around your bounding box in case you didn't have enough of those. We're going to loop through those. We're going to get all the cells in them, and we're going to do polytest utils. Polytest utils intersects the bounding box of the triangle with the here's a triangle. Is the AABB of the voxel cell in question. If it intersects and this voxel hasn't been turned on and made part of the arrangement yet, turn it on, make it part of the arrangement if we're debugging, show everything that we're, are we pruning it, are we putting it in, whatever. And then add the triangle to it. Now we also have this concept of a thing called a triangle stack. And I suppose it's as good a time as any to get into what this is, because I think that's the next, yeah, this is the next test. Triangle stack is part of the insidedness test. And the insidedness test is what's performed down here, the second pass. So again, remember, we had this problem where, well, we know that this is a voxel that's active and it's on the surface of the mesh. It was intersected by a triangle, but we don't know for sure if it's really inside the mesh, you know, if it can be part of the surface that we're going to end up building. In order to tell if it's inside, we want to look at the corner, all these 8 corners of this voxel cell, and see is any of the 8 corners inside the mesh. Actually, I guess, I mean, the real test is there a difference in insidedness between any 2 corners? If they're all inside, it's not a surface cell. If they're all outside, obviously it's not a surface cell. If there's any change, then it is a surface cell. Okay, so how do you do that? Well, actually, this might actually be easier to show graphically and then come back to the code in a minute. What we're going to do is we're going to do at each of these 8 corner vertices, we're going to perform a raycast against a subset of the polygons of the source mesh. And the way this works basically is you take your mesh and you're going to project it. It's like what do you call it? Not mark and sweep. Not swept fine. I don't know. It's a test where you're going to project the mesh into basically you're going to do a projection. You're going to lose a dimension. So in this case, we have XYZ data. We're going to project the mesh onto a plane, drop one of the dimensions arbitrarily, and then cast a ray along that missing dimension. So I chose Y because this is meant to work with caves and stuff. So there's quite a bit of XZ data, not a huge amount of Y data. So we're going to, for every vertex, and you can think of it like this. Like let's say this vertex cell is this one is kind of interesting. Let's say this vertex cell wants to know whether it's inside the mesh or not. I want to move this down. Let's say this would have been like here, for instance. And this one actually is inside. Well, how does it know that? It considers all of the polygons that sit within its XZ bounds. So again, on Y, any polygon in the source mesh whatsoever is added to in the triangles, added to a triangle stack, which is indexed by the XZ position of every voxel cell. So, and that's because we're doing that projection, we're throwing a dimension out, and then we're going to look along that dimension, more or less, to see what we're doing. So here we see that, well, it's hard to actually see, but you can see all these triangles in here going all the way down. For every vertex, for every voxel cell that's on this Y column, they're all going to be looking at this stack of triangles, and they're all going to, from each of their 8 corners, they're going to fire a ray on positive Y and ask how many times does that ray intersect, regardless of facing, the subset of the polygons that lie along my XZ bounding Y column. If that number is odd, then it assumes, regardless of which corner this happens on, it assumes that this is a legitimate, genuine, God honest, dyed in the wool, AAA Phillips surface cell. And now this is where the qualifications about using this with arbitrarily complex geometry come in. The geometry has to be closed. So if you imagine performing this surface test against a plane, it will say that you're inside the mesh when you're not really. You're just on one side of the plane or the other, but you're not really inside anything. So you won't actually be able to resurface that object. If the mesh has self-intersection, if there's weird geometry inside, extra poly is just kind of floating there, or anything like that, this thing is counting straight, pure, raw intersection. So if it hits twice on its way out, let's say that this inside corner, this corner down in here really is inside the mesh. Well, if they're in the actual source data was like some other hull or something like that in here, it would hit 2 polys on its way out of the mesh, and it would say, oh, well, that was even. I guess I'm not inside the mesh. It's looking for odd intersections. So the mesh has to be closed and convex, basically, and like not just a shell. Think of it as being a shell. It has to be a clean shell. If it's not, I mean, it's not going to break the whole process. And, well, it might actually end up breaking the whole process. But what you're going to end up with is gaps and holes and ugly stuff like that. All right, so that's the overview. Here's the code. We get the 8 vertices. I'll do a bunch of tests. We are casting along vector up. That's the direction you can see down here. Polytest utils intersects with this direction. And I'm using polytest utils. This is basically just a little class that, again, I included. This is like half sort of RMI code and half MSDN code. And actually, even one of the tests is a contribution from a Unity community member. A little bit more specific. They let you do some things, particularly regarding sidedness and the way you want your results returned and all that the Unity physics linecast and all that doesn't. You could probably use linecast, but I really like this suite that we have here, so using that. And again, you can see it's looking for odd number of hits. And then it's going to do this update to the corner mask. Corner mask, this is something you'll read about if you look at the old Marching Cubes papers. Basically, it's a bit field, and it's just a way of speeding up. I mean, not that the rest of this is optimized enough to be worth using, bit masks for speed, because the rest of this, the way I implement it, is very slow. It's just that the bit mask is actually very intuitive and very simple, and this is actually the easiest way to implement some of the later tests. So this uses the bit mask. Basically, each corner just has a field in the bit mask, and it's 0 or 1, whether it's inside the mesh or not. And that's, I just tried to zoom out the Unity way. That's not going to work. There you go. So now you have this, now you're in this position where you have sort of that Minecraft looking mesh we saw before. We know where all our surface cells are. We have vertices at the center of each of those surface cells, and we are interested in meshing this. But even though I showed it in a state where it had that kind of Minecraft appearance but wasn't smooth, it actually does it the other way around. It smooths it and then starts surfacing the object. Only if it's, this is a Boolean. This is really just there for instructional purposes, but whatever. So we're in here. The way the smoothing works is that it's going to basically iterate over, for each voxel, it iterates over all the triangles that it knew it intersected with early on in this process. And it's going to get the shortest, well, the closest point on those triangles to its center. Now, an interesting, again, bear in mind, constrained elastic surface nets, the constraint means that the center, the point that we're going to use for building the surface inside each voxel cell can't wander outside of the voxel cell. Because this is looking for the closest point on triangles that were bound by the cell, we know at this point, when we're done down here, we are still obeying the constrained elastic surface net rule. We're still constrained, in other words. So that's one pass of smoothing the mesh out, trying to conform to the underlying geometry. Here's the second pass. In this case, we're throwing all that out. This is where I looked at that thing. It looked like hammered bronze, and I said, nope. Going to just hit it with the smooth hammer, and whatever comes out is whatever going to come out. Now, the smooth hammer, I'll stop calling it that. I'm sorry. Smooth iterations, by default in the script, is set to 8. And at that number of iterations, there is a certain amount of volume loss. This is Laplacian smoothing, basically. So it's going to try and turn the object into a sphere, ultimately. Over, billions of iterations. It would take a long time, well, not billions, a long time to get there. You're not going to get there anytime soon. So there is a little bit of shrinkage, but it's really not particularly noticeable unless you're doing something very specific. Interesting point. To get around vertex limits or draw calls, or you just wanted for lighting or any other reason whatsoever to subdivide the meshes prior to voxelization. In other words, if you were going to take separate complex meshes and voxelize them independently, you're going to have gaps and seams because the way the averaging and everything works, they're not going to line up perfectly. Now, I do have like a seam finder and repairer script, which might actually be able to fix that. There are really two ways you should plan on addressing that if it comes up. The first is props. Band, rocks, bench, cut out a Boba Fett, whatever you got, put it on top of the seam so it's not as horrendous. And the second one is just to export these things. Again, it's actually fairly important to keep a very flexible workflow where you can move between programs. OBJ exporter, DAE exporter, which is, no one likes DAE, but it does preserve a lot more data than OBJ. Anything to get it back into Max to smooth those horrible edges out, and then be able to work with subdivided meshes. Or, because the poly count's actually pretty low, just make a big voxelized mesh and then use a divider script to turn it into smaller objects, based on some bounding cubes or something. All right, anyway, back to averaging. So we're going to do this Laplacian averaging, turn it into, just a smoother, get rid of that hammered bronze effect. Then we're going to start doing surfacing. All we're really doing here is we're initializing an array with the center points that we're going to be modifying from now on to build out the vertices of the final mesh. And then we go. Now, this part isn't commented particularly well, and this is like the magic part, right? Well, there's a bunch going on in here, but this is like sort of the hard part. This is the one I struggled on. And the one that I just said the other night, I was looking at this and I thought, wow, I really ought to finish this, so I decided to finish it. What is going to happen here? This is a little difficult. Maybe I should have had like a visual aid for this. Actually, do I have... I think I do. Let's see. Nope. Oh, and here's the post I had to update. Never mind. So if you imagine we have these center points and we want to connect them from, you know, one voxel cell center point to the other voxel cells around it. But there are only so many, because we know that there are going to need to be voxels next to one another on any axis along which it's going to build a surface. We also know some things about, like, this form has to be contiguous, and we've already done all the work mathematically to validate that it can be contiguous. So we really only need to look we only need to look at filling in certain patches. If you imagine, yeah, this is really hard to demonstrate, to talk through without showing it, but imagine a point that wants to connect to points in neighboring grid cells. Actually, just imagine it in 2D. Let's say that you wanted to be able to draw lines between grid cells in 2D. And let's say that you knew that they were going to form an enclosed contiguous surface when they were done. You don't have to consider top, down, bottom, you know, the top, bottom, and left and right neighbors. You only have to consider top and left or bottom and right. Because once you draw the lines between those, as long as you know for sure that this mesh is contiguous and that the resulting object is not going to have gaps or anything stupid in it, then just those tests will always fill in all the lines as needed. This is doing exactly the same thing. It's only looking at the left back poly, the right front. These might be lying. Yeah, these are lying. I think this might actually be worth taking out right away. Pretty sure that's right. Yeah, okay. It's only going to look left back, which is to say negative x, negative z, flat y, top right, and top front. Those are the only three polys any individual grid cell is ever going to try to create in the world. And they're going to line up because we know that the mesh is valid. Now, this is where things get a little involved. And again, I know this is a little boring, but it's worth talking through if you're trying to actually use the script or understand this stuff. And this is busier than some other implementations, but it's a lot less clever code. So I think it might be easier for someone to read, hopefully, unless you like clever code. I mentioned before corner mask, and again, that's where each corner is assigned an index in a bit field, and that represents a corner of the mesh. So here, that's kind of written out on a little cheat sheet. What each corner is relative to the center of the mesh. Is it minus, is it, lower on X, Y, Z, or higher, and what they are exactly. Now, we know we want to do the left and back test, and so what edge do we need to do when we're going to do that test? We need to test an edge between two corners, basically, two of these indexed corners. So if we're going to go left and back, that's, imagine you have a cube, basically, and you're going to draw a plane out, or like a unity plane, like a not a mathematical plane, but like a square, basically. You draw that out from the center out, to the object's left and behind it, like so, minus z minus x. That plane is going to bisect the edge sort of in the back aligned on y. And what that means is that it's the edge between the points negative x. We know it's going to be on negative x and negative z because we're going left and back. And we're going to bisect y. That means we want negative x, negative z, negative y to negative x, negative z, positive y, because we're going to bisect y because we're on the xz plane. So that means that the two corners we're interested in are 0, this one, and 4, this one. We want to do top right. It's kind of like it's going to go up and off to the side. It's going to go. So now we're on the now we're on the YZ plane, going positive y, positive z. Same sort of thing. That's going to bisect the x-axis, and it's going to do it, on positive y, positive z. So that's going to be 7, which you can see here is. I'm sorry. It's going to bisect z on positive x, positive y. And you can see that we have that here, 7, 6. That's crossing z on positive y. Order matters, by the way. You notice this one is 0, 4, this one's 7, 6. Order matters. The order in which I added these indices is kind of arbitrary. The order in which they are tested down here, because this impacts winding order, is not arbitrary. So it's important. You might have to do a little trial and error to get it, but it is important that order matters. The last one is more the same. Now, the neighbor offsets. So again, we're going to go left and back. Now the thing is, we're building a quad though, so we don't just need our neighbor to the left and neighbor to the behind, you know, minus x neighbor and minus z neighbor. We also need the minus xz neighbor. So we need 3 neighbors in order to do this. And that one's not technically adjacent. It's the diagonal neighbor. So I store also for each of these tests, for each edge we're going to test, we also want neighbor offsets. Now these are cell space XYZ integer offsets from the current voxel cell XYZ position. And so there's a whole lot of stuff. But what that means is, if I'm at, you know, x coordinate, if I'm at XYZ coordinate 2, 2, 2, I want to apply these integer values for my first neighbor. I want to look this far away. For my second neighbor, I want to look this far away. For my third neighbor, I want to look this far away. So this is neighbor A, neighbor B, neighbor C. These are the XYZ integer cell space offsets. In other words, the ID offsets from the current cell's ID as we're going to march through and do this. So because we're going to march across every voxel in our subset of voxels that are useful. And we're going to do this test. And the test is, we get the neighbor ID, again, based on neighbor offsets. Ignore this neighbor index is unnecessarily complicated. The point is that we're going to get, based on these offsets, this neighbor to the left, this neighbor behind us, and then this neighbor who is to the left and behind us. That's neighbor ABC. We're going to make sure that none of these guys are null and that none of them are not surface voxels. And then we're going to need to decide, this is where we're doing that surfacing. We're going to decide, okay, we're building a polygon, or we're going to build 2 triangles. We have a quad. We have 4 vertices. We have a self and 3 neighbors. We have 4 vertices. And what we want to know is, how do we want to use these 4 vertices to create 2 triangles such that they look better than that horrible daisy field I showed in the example comparing naive triangulation to quad triangulation. We assume that we can be naive about it and draw the triangle that this was already going to draw. And that's basically the one where the neighbor in the back, you know, the one that's not adjacent, is not the closest point of the 3 presented to the self. In other words, so if you're in a voxel cell, its center is further from the one that's in the corner than it is to the other 2 by its side. If it turns out that's not true, if this is the corner one, you know, NC, if that node point minus your current node point is closer than the other pair, A minus B, then you know that actually, no, you do want to split, because you can. There's only 2 splits you can make. You can make the split between A and B. You can make the split between self and C. If self and C is shorter than the split between A and B, make that one. That's it. That's the meshing rule. And then this is some bitwise to make sure that we're crossing the edge. It matters, by the way, the reason order matters is it matters which of these corners we actually cross. If you crossed both, that you can't split that edge. If you do that, you'll end up with fins. These triangles that well, in this case it'll be polys that leave gaps. If you don't test to make sure that only one of the 2 corners of the edge you're bisecting is actually a surface edge, I mean, that has to be a surface edge. In other words, it has to penetrate the surface of the mesh. If it's all inside, it doesn't work. So we make absolutely sure that if it's both, we don't do anything, because we don't want that case. We only do it if it's one or the other. And depending on which one it is, our winding order changes. See here, we go self BA, down here we go self AB. Same thing for the other, that's one triangle, and the other one works exactly the same way. Depending on whether we decided to do our split, you know, with a triangle being formed between self AB or between self AC or self BC, right? So that's just the winding order. This block is very complicated. You could probably spend a day talking about this by itself. You could probably also spend a week optimizing this, or a day, if you know, whatever. This could be done better. It could be clearer, but this is kind of like, again, this is one of the hard parts, so I wanted to explain that in some detail, especially since this is not commented. The rest of this thing's commented pretty well. You can get by. This is just like, you know, what the hell's he doing? So hopefully that will help explain what that's doing. And then magically you're done. It's just time to build a mesh. And whatever it is I'm doing down here. Oh, this is just the planar, again, that planar Y map. Normals are recalculated, tangents are recalculated, and there you go. That will do it. And I'll save and hope that I didn't make too many stupid changes that break this. So that is the retopologizing script. I think it might actually be interesting to talk about the box mapping script in another video. Yeah, I'll save that for another video. So there you go. And here's the tool. And it is some pretty interesting stuff. Very flexible, very useful, can obviously branch out into a lot of different directions. And let's just take one more look. Just one last parting glance. Again, generate our box UVs. This again, this is slow, and it generates a separate mesh. It probably doesn't have to. I mean, obviously you can change it if you want. You can also speed it up if you want, and if you do, please let me know. And then we're just going to invert the normals. Slap a Cave texture on there because Cave Johnson is pretty much the coolest guy there ever was. Go down to our dude, hit the right button. There we go. Ah, that's so nice. This reminds me of like, well, this is actually more like Black Rock Depths. The whole thing kind of reminds me of Oncology. Yeah, I can see it's in Black Rock Depths, man. Yeah, yeah. All right, that's that. You might have a lot of questions. Of course, you can always leave comments on my website, Adrian's Wall. That's just, you know, Adrian's Wall, my name. Really freaking creative name there. Or here in the YouTube video, or on the Unity forums, where this will probably be posted on the Unity forums. And if your question isn't too hard or make me look stupid, I will try to answer it. So I hope you enjoyed this. Hope it made sense. Hope the tool is useful. And we will speak again in the next video. Thank you for watching.